On to question 2. Question 2 is somewhat simpler than the first question. There's 3, again, fairly separate parts, but it doesn't get much simpler than part 2a. So we'll follow our usual mantra of drawing a diagram, stating variables. Cylindrical rubber pad of 100mm diameter. And remember, we're trying to convert units as we draw the diagram. 40mm thick. Compresses 6mm. So effectively this is our original length, and its change in length, delta L, is 6mm, 0.006. When supporting a mass of 200 kilos. So we're generally not interested in masses, so that'll be 200 times 9.81. See question 1 if you want to know why that is. That's how we convert. So 200 times 9.81 is 1962. Which is our force. And it wants to know the Young's modulus of the rubber, assuming Hooke's law to apply. Now, all Hooke's law basically says is the force is proportional to the distortion. So it's the straight bit of the stress strain curve, this bit here. So in other words, assume that your normal formulas work, which is just as well. So let's state our formulae next. So we know that Young's modulus, and as soon as you see that word, you can pretty much say Young's modulus is stress over strain. Unbelievably, this is given in your formula sheet. You should really remember this. Stress is given by force divided by area, and strain is given by change in length over the original length. And questions don't come much simpler than this. So let us work out the stress, work out the strain, plug it into this this equation here to find out the Young's mod. So stress is equal to the force, we calculate to be 1962, divided by the area. So we know that the area of a circle is pi r squared, which will be equal to, well, I'll write it down here, which will be equal to pi times the radius. It's got a diameter of 0.1, so 0.05 squared, and that is equal to, type that into my calculator, this very large value, so 249,809.6 I'll round up to. Our strain is equal to the change in length over the original length, so that'll be 0.006 meters, 6 mil, divided by 40 mil, 0.04. Stick that into the calculator, and we get 0.15. And to calculate Young's modulus, that's going to be stress over strain, which is going to be equal to 249,809.6 divided by 0.15 is equal to 1665397.33, pascals. Now, if I have my nice Casio calculator, I'd just press the ENG button to convert that, but as I don't, I'm going to do it manually. 1, 2, 3, 4, 5, 6, which will equal 1.67 megapascals, which is obviously 1.67 times 10 to the 6. Quick check against the answer sheet, and we find that is correct. On to question 2b, which is a little more involved. When we read through this question, we see that there's a cantilever beam. It's got various forces along its length. Unusually, there's a tie bar supporting the beam, and we need to find shear force and bending moment diagrams. Now, in some of my other work through videos, we've considered a simply supported beam, so something supported at either end. Various forces will be given some kind of shear force diagram, might look like that. A bending moment diagram might sort of look like that kind of thing. And it's relatively straightforward. Cantilever beams are a little different. I'm just going to do a very, very rough sketch to show you the method we're going to look at this. So when doing a cantilever beam, then I'm going to recommend that you sort of draw from the right hand side. That's the wall end, or the built-in end as they call it. We'll have a beam extending outwards. It's 3 meters in length. It's got a ton at 1 meter. Now don't be sucked in by 1 ton. That is 1,000 times 9.81. So we've got a force there. We'll just call it F1 for now. At 1 meter, and we've got a load at 3 tons at the free end. I'll call that F2. However, there's a tie bar supporting the beam. So I suppose a tie bar might be some kind of bolted on structures, maybe securing it to a roof perhaps, but we're not interested in that fluff. All we are interested in is the fact that there is a counterforce to the F2 at 15,000. So let's chuck some numbers in here. This will be 1,000 times 9.81, which would be 9,810. F2 will be 3 tons, and this is 3,000 times 9.81, which works out as 929,430 minus 15,000. Which ends up at 14,430. So the net result is there's one force acting with this magnitude, 14,430 down. So it's a little simpler once you draw a quick rough sketch. However, rough sketches are not going to help us solve the actual task itself. These types of question reward attention to detail and neatness. So let's start by drawing some very faint lines. So we're going to have the wall end. Oops. We'll have a force at about 1 meter. Now this doesn't need to be to scale, it doesn't need to be in proportion. And then at 3 meters, so that's roughly 2/3 and 1/3. So now that I've got my rough guidelines, I can start drawing in. So I'm going to at the start have a diagram. Then I'm going to have my shear force diagram. And then my bending moment diagram. So this is my beam. And we've got a force of 1 ton, so 1,000 kilograms times 9.81. Which is equal to 9,810. And then I've got a force of here. Now, I'm in two minds whether to redraw that mini sketch that I did, but I'm simply, at this case, going to write 29430 minus 15,000, just to show the examiner what I've done there. She's going to be 14430. Okay, so this is our diagram. We're then going to do our shear force, thus getting this bit of the question correct. So I'll draw an axis, and literally I'm just going to trace down from here. So I'm going to go 14430. Oops. I can draw that line straight. So this arbitrary point here will be 14430. I'm going to go across to the next point of interest. There we go, like so. And I go down to 9810, so 14430 minus 9810 comes out at 24240. What happens there? 24240, and that's just come from 14430 add 9810. I suppose this is all negative, isn't it? And then I go across to my next point of interest, and there is obviously at the ends of the beam no shear force, so that joins up there to 0, and that's our shear force element done. Now there's various ways of calculating the bending moment diagram. I tend to do it in a slightly different manner than most. Bending moment, if we actually think what a moment is, a bit like torque really. Think of the old small spanner undoing a nut versus the enormous spanner doing a nut. You choose the enormous spanner because you have a greater torque or moment, because for the same force you have a much bigger distance from the pivot or the nut. So bending moment, or the torque, same thing in effect, is force times distance. Okay, so how does that help us? Well, if the bending moment is simply force times distance, then we have the forces in this axis. We know that this section here is 14430, this section is 24240. We also know that this is 1 meter, we know this is 2 meters. We have a force times the distance. So it follows that if we work out, use a different colour, so the area of this section, and we work out the area of this section, then we will in effect calculate the bending moment, because the area is force times distance. Bending moment is force times distance. So let us do that. So in this case, the bending moment will be equal to a distance of 2 times the value here, which is 14430, which is going to be equal to this value, 28860. So on our, well, let's do the second one first. So this one is going to be a distance of 1 times the distance of 24240. That's simple. Even I can do that in my head. The area is equal to 24240. Okay, so axis in. Oops. Try and do your axis a little lighter in colour or in tone. Okay, so it's a bending moment at the end of the beam here don't need to worry too much about. So we start here, and we're going to go down to 28860. This point here, 28860. Next, we're going to add on this value here. So 28860, add, so these two added together will be the next bit. And that turns out to be 53100. So there we have the shear force diagram and bending moment diagram without doing too much in the way of mathematical calculations. And that is just a function of working out the area, because area is bending moment. So a bit of a different way of approaching that, but one I prefer. On to part C. Part C, a hydraulic press is used to lift a mass of 10 tons. The diameter, so we're talking about diameters of pistons. Right then, this is a master-slave cylinder setup and is Pascal's principle. You should be able to recognise that from Pascal's principle. So let's set the question up and attack it. It's actually a relatively simple, straightforward. So a hydraulic press is used to lift a mass of 10 ton. So we've got a small diameter and a large diameter piston. So let us sketch that now. It's a very small diameter, but never mind. Right, so I have my two pistons linked by a rudimentary pipe of some kind. We've got a master and slave cylinder in effect. And from our formula sheet, we know that Pascal's principle says that F1 over A1 is equal to F2 over A2. So this, the force exerted here, will be F1 and F2, and then we'll have, assume these things, pistons tend to be cylindrical. In fact, it says diameter, so yeah. We'll have an area here, so we've got area 1 and area 2. So let's just first calculate area 1 and area 2. Just realised I put the arrowhead on the wrong way around here. Well, so mass of 10 ton, so that'll be 10,000 kilograms times 9.81, which is going to be 981. $98,100. Let's work out the areas. Area being pi r squared, so A1 is going to equal to pi times the diameter of the load piston is 252. The diameter of the pump piston is 714. How strange, they seem to have this jack backwards. Generally you use the small piston to drive the large piston. There's a whole point. They appear to be using this setup in order to make life more difficult for themselves. How strange. Anyway, we'll do what we're told. The load piston, which is this end, so that's going to be pi r squared, which is going to be pi times r squared. So that's the load piston is 252. So that'll be a 126 mil divided by 1,000 is 0.126. And that comes out as 0.049, near enough 0.05. At the pump piston is 714 mil. So 714 divided by 2 is 357, divided by 1000 to get it in millimeters is 0.357, to get it in meters rather. Square that, times it by pi, and we get an area almost exactly of 0.4. So let us use Pascal's principle, and we will say F1, which is the unknown force. So F1 over 0.4 is equal to F2, our known force, 98,100, divided by A2, 0.05. Let us resolve this then. So I'm just, since it worked successfully in the last question, I'll literally move this up here. Times in both sides by in effect. Let's process this calculation. So we'll have 98,100 divided by 0.05 times by 0.4 equals 78,800, which is 78.48 kilonewtons. Now I've just reviewed the answer given in the answer guide, and the answer is given as 12.26 kilonewtons. And you will get that answer is if you actually apply the swap these two round. Now the way I've read that, the diameter at the load pistons, this is where the load is 252 millimeters. Which is quite small. The diameter of the pump piston, so this is the pump, this is where you're going to actually start pumping in order to lift the load, is 714 millimeters. In other words, quite big. So there we have pi r squared, we get 0.4 here, and 252, we get 0.05. So the way I've interpreted that question gives this, the answer guide gives that. Obviously I think I'm right in the way I've interpreted the question, but the intention of the question is that it's using a traditional hydraulic jack style. In other words, small at the master side and large at the slave side. I would be interested to know if you think I'm wrong. Do let me know in the comments. But I think you can't argue with the way that's phrased. It's phrased as though it's that way around to me. Please explain to me why I'm wrong. But if you process it with them being the way around that they intended, in other words, small for pump, you end up with 12.26 kilonewtons, the correct result.